evaluating this integral, we still have to account for the area dx times dy. We're expressing this in terms of u and v, but we still have to get this area right. Otherwise, we're going to be evaluating an entirely different integral. So how do we take dx times dy and express it in terms of u and v? Well, here's what we have. We have our rectangle, u and v, and it's approximately mapped into a parallelogram. So here we have this point. We'll call this ui minus 1, vi minus 1. Here we have ui vi. So we're carving up a domain into several subdomains like we normally do. Vi and ui vi minus 1. So if we take a look at what's happening with these 4 points that are mapped over here, we get roughly a parallelogram. So this point is going to be g of ui minus 1, vi minus 1, and h of the same point. Right? And then this point is going to be g of ui vi, that's the x-coordinate. Y-coordinate is g of h of ui vi. So what is the area? So we can think of this as roughly dx times dy, but we need to express it in terms of u and v. So if we can figure out the area of this parallelogram that is obtained from this rectangle of dimensions delta v and delta u, then we know what to multiply our integrand by. So it boils down to computing the area of this parallelogram. Now this parallelogram is defined by 2 vectors. I'll call these, let's see, here we're changing, all right, RV and RU. Okay. So the vector RU, we can write down what that is. So that's going to be, the x-coordinate will be g of u I, vi minus 1, minus g of ui minus 1, vi minus 1. So that's the x-coordinate. Then the y-coordinate is the same thing, only it's a difference in h. Okay. Now, so the u's are what's changing in both cases. Right? The v's are not. But ui minus 1, that's delta u. So what we can do with each of these components individually is apply the mean value theorem. So this difference in function values is actually going to be equal to the partial derivative of g with respect to u, evaluated as sum u in between, v stays the same, and then same thing for h, times the difference in u's, which is delta u, which I'm just going to pull out. So recall the mean value theorem says f of b minus f of a over b minus a is f prime of c. So where c is between a and b. So that's all we're applying here. Since only u is changing, v is not, then we're just looking at a partial derivative with respect to u. Okay. All right. So the difference in function values, actually what I'll do is I'll write this a little differently. I'll just multiply both sides by b minus a. So now this is more closely resembles what I have down here. So the difference in function values is equal to the derivative at some point in between times the difference in the arguments. Here we're looking at ui and ui minus 1. The difference between those is delta u. That's why there's a delta u sitting out here. And both components have that. So that's why I'm writing it outside. Okay. So I want to make sure that we're good to go with this before I continue. That's also in the notes. Okay. All right. So a vector that defines this edge is equal to this, and now we're expressed in terms of the partial derivatives with respect to u. The other edge, RV, you can do the same thing, only now you're looking at a difference in v. So, or change in v rather. So RV is partial of g with respect to v, ui minus 1, vi star, partial h with respect to v, ui minus 1, vi star, delta v. Okay. So now we've defined the edges of this parallelogram in terms of u and v, and we see it involves the partial derivatives with respect to u and v. So, written another way, this is partial of x with respect to u. This is partial of y with respect to u, because x and y are defined from using g and h. This is partial of x with respect to v. This is partial of y with respect to v. All right. So we have the edges, but what we really want is the area. How do you compute the area of a parallelogram? If you have vectors that define these adjacent edges.
Cross product?
Cross product.
Yes.
Yeah. All right.
Contributed.
Because I was thinking, remember something from last semester. Yeah, so the area is a cross product of RU and RV, where what you need to do is, cross product is defined for vectors in 3 dimensions, so you would just add a third component to each of these, which would just be 0. So I'll write out the vectors again in a shorter form. So what we have is dx du, dy du, delta u, so that's one vector, cross, and then, like I said, I'll add a third component that's 0, delta u, cross delta x, delta v, delta y, delta v, 0 times delta v. So how do we end up computing the cross product of these particular vectors? Keeping in mind that we have zeros in the very last component.
Carefully.
Well, of course, but so what do you do? Actually, how I often did this last semester, I would write one vector on top of the other, and then you'd be,
Oh,
yeah,
That's the.
yeah, yes, that operation. Okay, so you remember the name of the operation, you didn't remember what it entailed. Okay, but now you do?
Yeah, we do. It's coming.
Yeah. Oh yeah, that's that rule for 3 by 3 determinants that you mentioned last time. And it's terrible that it only works for 3 by 3. But bottom line is we can use it here. So what you end up getting is we're going to take a magnitude of all this at the end. So you get 0, 0, and then xu yv minus xv yu.